Nuclear power is the use of nuclear reactions that release nuclear energy to generate heat, which most frequently is then used in steam turbines to produce electricity in a nuclear power plant. Nuclear power can be obtained from nuclear fission, nuclear decay, and nuclear fusion reactions. A nuclear power plant is a thermal power station in which the heat source is a nuclear reactor. As is typical of thermal power stations, heat is used to generate steam that drives a steam turbine connected to a generator that produces electricity. What is generation for reactor? Fourth generation nuclear power, or Generation 4, implies a system of reactors and nuclear fuel cycle facilities, fuel fabrication plants and reprocessing facilities that together may manage the weaknesses often associated with nuclear power of today. Generation 4, nuclear energy systems deployable no later than 2030 and offering significant advances in sustainability, safety, and reliability, and economics. For the first generation, it is the early prototype reactors which is in between 1950 to 1960. The second generation is the commercial power reactors which is in between 1970 to 1990. And Generation 3 is the advanced LWRs which is the continuation of the second generation until 2010. Finally, the advancement in the nuclear reactor is the Generation 3 Plus and Generation 4, which is started from 2010 and still continuing until now. This advancement is still in the research and it is expected to develop a good results and can be useful for the progress of the world in the future. The lead-cooled fast reactors, LFRs, feature a fast neutron spectrum, high-temperature operation, and cooling by either molten lead or lead-bismuth eutectic, LBE, both of which support low-pressure operation, have very good thermodynamic properties, and are relatively inert with regard to interaction with air or water. They would have multiple applications including production of electricity, hydrogen, and process heat. System concepts represented in plans of the Generation 4 International Forum, GIF, System Research Plan, SRP, are based on Europe's ELFR lead-cooled system, Russia's Brest OD300 and the SSTAR system concept designed in the US. Numerous additional LFR concepts are also under various stages of development in different countries including China, Russia, the USA, Sweden, Korea, and Japan. Lead, Pb, or lead bismuth, PBBI, as coolant. Lead is not chemically reactive with air or water and has lower coolant void reactivity. 650 degrees Celsius to 800 degrees Celsius outlet temperature. Small transportable system 50 to 150 megawatt electrical. Larger station 300 to 1200 megawatt electrical. 15 to 30 year core life option. Distributed electricity generation. Hydrogen and potable water. Replaceable core for regional fuel processing. High degree of passive safety. Proliferation resistance through long life core. The use of lead as a coolant offers several important advantages in this regard. In an interesting recent analysis, Toshinsky et al. 2011, considered the question of stored energy in various types of reactor coolants. This analysis highlights several important advantages of lead coolants, with respect to the availability of energy which is thermal, pressure-related, or chemical, to exacerbate accident conditions whether initiated by natural phenomena or not. As low-pressure coolants with relative chemical inertness, lead has innate characteristics that enable a high level of passive safety and suggest more benign end states in the case of unforeseen accident conditions. The concept is generally very similar to sodium-cooled fast reactor, and most liquid metal reactors have used sodium instead of lead. Similarities between thermal reactor and fast reactor. Both are nuclear fission reactors, these are not nuclear fusion reactor. Enrichment of natural uranium with uranium-235 isotopes is required in both type of reactors, however, the percentage of such enrichment varies widely. PHWR can be operated at natural percentage of uranium-235. Chain reaction is very much desired to continue heat generation irrespective of the type of reactor. Irrespective of reactor type, the uranium dioxide, UO2, in the form of rod or pellet is commonly used as nuclear fuel. Differences between thermal reactor and fast reactor. Thermal reactor, fast reactor. In thermal reactors, the fission chain reaction is sustained by the thermal neutrons, while in fast reactors, the chain reaction is sustained by fast neutrons. Moderation is required to slow down the prompt neutrons produced in one fission reaction, in order to make such neutrons suitable for further fission. No such moderation is required, as fission is sustained by the fast neutrons. Based on the design, thermal reactors utilize either light water, or heavy water or carbon dioxide as coolant. Fast reactors utilize liquid metal, which is liquid sodium or liquid lead as coolant. Thermal reactors require low-enriched fuel. Typically, light water-based reactors and gas-cooled reactors require 3 to 5% enrichment, while heavy water-based reactors require no enrichment, which is natural uranium can be used as fuel. Fast reactors require comparatively high enrichment, to increase chances of fission by fast neutrons. Fast reactor fuels are usually 15 to 20% enriched. Nuclear breeding does not take place in thermal reactors. Nuclear breeding occurs in fast reactors. Finally, thermal reactors generate large radioactive waste, while fast reactors help reducing radioactive waste by continuously disintegrating heavier isotopes. The LFR is an advanced Gen 4 reactor type that offers significant advantages in achieving the goals set by Narek-Jif 10 years ago. Among the 6 reactor types considered to be promising by the NERTAC-GIV, the LFR may well offer the best combination of characteristics and advantages. The events at Fukushima Daiichi have increased international attention to the need for advanced reactors to be resilient in the face of unforeseen and/or severe accident conditions. In this context, the intrinsic characteristics of lead as a coolant as well as the potential to exploit passively operated heat removal from lead-cooled systems leads to particular advantages of the LFR as an advanced reactor technology to meet present and future needs.